Now let us see how an inductor modifies the behavior of a circuit. Imagine we have a voltage source where our input is 4 e to minus 20t for all time greater than 0. If our output current, I of t, is equal to minus 1.2 e to minus 20t minus 1.5 amps for all t greater than 0, and the initial current within our inductor is minus 3.5 amps, we want to be able to determine the inductance and resistance of the circuit based upon these operational parameters. For us to begin, we'd have to recognize that there's current leaving our voltage source, and thus we would have current running through our resistor and current running through our inductor. To solve this, we construct Kirchhoff's current law at node A, where we'd have I of t entering, and I of R and I of L exiting, where I of R is our current running through our resistor, and I of L is our current running through our inductor. There will be current running through our inductor since there's a time rate of change of voltage existing across. If we substitute in our constitutive equations for a resistor and inductor, we have the following. Our source current I of t is equal to our current running through our resistor, which is our voltage potential, V of t, per our resistance, plus the current running through our inductor, which is our initial current, plus 1 per L, the integral from t naught to t of V of tau d tau. Now we can substitute in our givens. Our current leaving our voltage source is equal to minus 1.2 e to minus 20t minus 1.5 amps. That is, we're going to have a constant minus 1.5 amps, and we're going to have a minus 1.2 e to minus 20t. As time tends to infinity, this portion of our current is going to tend to 0. Now our voltage potential across our system is 4 e to minus 20t, and this exists across both our inductor and resistor. So our current running through our resistor is 4 e to minus 20t per R, and then the current running through our inductor is going to be 1 per L, the integral from 0 to t of V of tau d tau, where our voltage is 4 e to minus 20t dt, and we have initial current of minus 3.5 amps. Now, we have to evaluate the integral. 1 per L, the integral of 0 to t of 4 e to minus t d tau, is equal to minus 4 per 20L e to minus 20t, evaluated between 0 and t. Thus, our integral is evaluated as minus 4 per 20L e to minus 20t less 1. Now, if we regroup all our terms, our KCL equation becomes minus 1.2 e to minus 20t minus 1.5. That is the current that was leaving our voltage source. This is equal to 4 e to minus 20t per R, the current running through our resistor, minus 4 per 20L e to minus 20t minus unity, minus 3.5, the current running through our inductor. To solve this, we have one equation and two unknowns. Thus, we're going to group our exponential and non-exponential terms. Our exponential terms have a time dependence. That is, as time tends to infinity, these terms reduce to 0, and our non-exponential terms are going to be constants. Thus, equation 1 has our exponential terms. Minus 1.2 is equal to 4 per R minus 1 per 5L, all multiplied by e to minus 20t. These terms represent our time-dependent behavior of our circuit. And then our non-exponential terms, i.e. our constants, is minus 1.5 is equal to 1 per 5L minus 3.5. Thus, we have two equations and two unknowns. We can solve for L. In doing such, we see that we'd have 2 is equal to 1 per 5L, or L is equal to 1/10 of a Henry. Lastly, we can solve for R, now that we have L. If we solve for R, R is equal to 5 ohms.